In previous class, I mentioned the relation between acceleration due to gravity g and radius of the earth r. I told you that if radius is less, the value of g will be more, and if radius is more, value of g will be less. But now we are going to talk in detail about the same. What is found practically by observation, by different experiment, what is found? The value of g is inversely proportional to the square of the radius of the earth. This statement is true. Mathematically we can say this way, this notation g is inversely proportional to square of the radius of the earth. But how can we prove this mathematical relation? We can prove this statement or this mathematical relation between g and r with the help of mathematical derivation. Now I am going to derive this g is inversely proportional to r square. Look at this. Let's say this is earth and its mass is denoted by capital M. And there is a body lying on its surface. In comparison with the earth's mass, the mass of this body is very less. That's why it is denoted by small m. And let's say this is the radius of the earth, which can be denoted by capital R. Now I am writing the same. Mass of earth, let's say capital M. Mass of the body lying on the surface of the earth, let's say small m. Radius of the earth, let's say capital R. After this was symbolized. Now, according to Newton's law of gravitation, as I told you in one of the previous video clip, the gravitational force F is equal to g m1 m2 by d square. It was told in previous video clip. Now I want to fit the same equation in this case also. The gravitational force between earth and this mass is also F, gravitational force, and the gravitational constant remains same, capital G, but in place of m1 and m2, here we have capital M and small m. Capital M is the mass of the earth and small m is the mass of the body lying on its surface. Capital M and small m in place of m1 and m2. Now in previous case, I told you about the distance also. The distance d was taken from center to center. That's why it was denoted by d. But in this case, the distance between these two bodies is actually the radius of the earth. That's why in place of d, we can say r and square of the radius of the earth. This is, let's say, equation number 1. It's not necessary to mention this, but I recall this to get this relation properly. Okay, you are taught somewhere about the Newton's law of motion. According to Newton's second law of motion, we know that F equal to ma. Mass force equal to mass into acceleration. But here the acceleration is acceleration due to gravity. That's why I'm writing g. F equal to mg. It is given by Newton's second law of motion. It can be recognized as second equation. Now combining equation 1 and 2. Combining equation 1 and 2. We get what? F equal to g m1 g m by r square. F equal to g mm by r square. F equal to mg. It means mg equal to capital G, capital M, small m by r square. Here m cancel each other. Now the remaining equation says that acceleration due to gravity depends upon capital G. It also depends upon capital M. It also depends upon radius of the earth. But we know that capital G is a constant. This value of G is not dependent on capital G. It doesn't make any difference to small g. In the same way, the mass of the earth is also a constant. Look at this. If a body is dropped at pole, G is 9.83. If the same is dropped at equator, g is 9.78, reduced. This reduction of g is not because of change of mass of the earth. Mass of earth remains same when we drop a body at pole or when we drop the same at equator. That's why here g, capital G, and m are constant. So g doesn't depend upon these two. G only depends upon radius, because radius is not constant. At pole it is less, at equator it is very high. In the middle of these two, radius is different. That's why if this equal to sign is removed, because of the removal of this capital G, we can write G is inversely proportional to R square. This way we can prove that acceleration due to gravity is inversely proportional to square of the radius of the earth.